Come on, my dears, we proceed further in chapter number 2. Last time we had seen about capacitor. Remembered? Capacitor is very important electrical component which is utilized in circuit for having storage of electrical energy. Correct? How did we define capacitor? Listen. An isolated system made up of two conductors having arbitrary shape and volume kept near to each other and yet separated from each other, having equal magnitudes of unlike charges, is called a capacitor. Correct? Fine. Normally, the two conductors used in the capacitor are known as plates of a capacitor. Plates of a capacitor. And in our syllabus, we have to study about that capacitor in which the plates are kept parallel to each other. We call it parallel plate capacitor. Okay? If the medium between two plates is not specified, then by default you should take the medium as air medium, and if no medium is there, you may take it as vacuum. Okay? So better we should say parallel plate vacuum capacitor or parallel plate air capacitor. Correct? But normally, just for the sake of simplicity, we do not speak air or vacuum, we simply say parallel plate capacitor. Correct? If the medium between two plates is not air medium, if it is some other medium, then it is called dielectric capacitor, about which we will study later on. At present, we want to study about parallel plate air or vacuum capacitor. Okay? Fine. Now, before we go for derivation of formula of its capacitance in this question number 18, we will definitely see the theoretical part given in the textbook, but before that I would like to explain you something extra about how does a capacitor get charged. How do we carry out the charging process of a capacitor? I am showing you. Try to understand this phenomenon of charging of a capacitor, it will help you later on. Consider a parallel plate capacitor. Okay? In this capacitor, compared to distance between two plates, the length and breadth of both the plates are kept very large. They are kept very close to each other, quite parallel to each other in this situation. Okay? Now what we do? We just connect a battery across these two plates. Okay? Suppose positive terminal of the battery, in this symbol you must have remembered, longer terminal is positive, shorter terminal is negative. Suppose positive terminal of this battery is connected with this left plate, okay, and negative terminal is connected with this right plate. Fine. Now what will happen? These are metallic plates, they have plenty of free electrons. Now because this plate is connected to positive terminal of the battery, it will so happen that free electrons from this plate will be attracted towards this positive terminal, and hence they will start displacing, they will flow through this conducting wire in the external part of the circuit, and then after entering inside the battery, they will receive energy, and then after those electrons are deposited on this right plate. Okay, fine. Now tell me, in this process what has happened? This plate has lost electrons, means it has lost negative charge. So I must show here plus sign just to indicate the presence of positive charge. This plate now becomes positively charged, and the electrons which have been deposited on this right plate will make that plate negatively charged. So I am putting here negative signs. Okay? You must take care of that point. As many positive signs you are showing here, that many negative signs you must show here. Correct? Because whatever is the quantity of positive charge here, same is the quantity of negative charge here. Got it? And here what will happen? As more and more electrons get transferred from this plate to this plate, it will so happen that here positive charge will go on increasing and here negative charge will go on increasing with the same amount. Okay, fine. My dears, you must show the presence of charges on those two faces which are inside and which are facing each other. That's why those two faces which are facing each other, which are inside, I have shown purposely with different color. Look, this face I am showing with blue color, correct, which possesses this positive charge, and here the face which possesses negative charge, here also I have shown with the blue color. So those two faces which are inside and facing each other, they only have charge. For this plate, this back side does not have any charge. For this right plate, this side, right hand side face shown with the pink color, does not have any charge. Only blue colored faces which are inside facing each other, they have charge. Okay, fine. Now how long this charging process will continue? The process whereby we can deposit charge on the plate of a capacitor is called charging process. But how long will it continue? Look, as more and more positive charge is established here, here more and more negative charge is established, and thereby the potential difference between these two plates keep on increasing, correct? At one stage, potential difference between these two plates will become equal to terminal voltage of this battery. At that point and then after, no more electrons get transferred from this plate to this plate. So you can say charging gets stopped. Okay? By that time, the capacitor is said to have become fully charged, completely charged. Okay? Theoretically, it takes infinite time, theoretically. Practically, after pretty long time, the potential difference between these two plates nearly becomes equal to this terminal voltage. Okay? In all the examples now onwards and in all the theories, when we say capacitor, we mean to say completely charged capacitor. Okay? By default, you must take it that way, correct? Fine. So this is how capacitor can be charged. Fine. There is one more method you can make plates of a capacitor charged. What is the second method? That is given in the textbook. I am showing you that also. Consider parallel plate capacitor. Here what we do, first plate we take already right from beginning positively charged plate. So plate number 1 has positive charge right from beginning, and that positive charge I am showing here, correct? Actually it is spread over entire surface. Here also it has positive charge initially. When it does not have in the surrounding region other external electric field, at that time it will have charge spread uniformly over its entire surface. But now what we do, we bring another plate, say second plate, which is electrically neutral, very close to this plate, and we keep it parallel to this plate. Fine. Now what will happen, I am showing you. This plate is electrically neutral, but in that also there are plenty of free electrons. So depending upon the magnitude of this positive charge, equal number of negative charge will get established here on this inner face, and that is why I am showing here presence of electrons, negative charge, correct? And the charge which was here spread over the entire surface now gets deposited only on this inner face. Okay? So what will happen, I am showing you. The electrons, they will just repel electrons from this face, and so those electrons will be neutralizing this positive charge here. So this face now does not have any charge. Charge is there only with this face, and whatever is the positive charge here, same is the negative charge here. And how do we remove negative charge on this face? For that purpose, what we do, we just make it earthed. We provide connection through this conducting wire to the ground, and then the electrons which are present here will be entering into the ground, because ground has zero potential compared to negative, 0 is higher. Compared to negative, 0 is higher. So electrons would prefer to go from here to here through this conducting wire, because they have a tendency to move from lower potential to higher potential. Compared to negative, 0 potential is higher potential, correct? So when electrons have gone inside the ground, there are no more electrons here, fine. So here inner face has negative charge, here inner face has positive charge. On both the faces, charges are opposite with polarity but equal in magnitude. So that's why I am writing here plus capital Q, here I am writing minus capital Q, correct? So this is how you can have both the plates of a capacitor having equal magnitudes of unlike charges. Got it? Fine. Now what is the capacitance of such a capacitor? I am showing you. If you consider this face having positive charge with uniform distribution, then what is the electric field produced by infinitely extended plane of charge? Come on, having uniform surface charge distribution, what was that? Studied in first chapter, capital E equals to sigma upon 2 epsilon 0. Capital E equals to sigma upon 2 epsilon 0. Fine. Look here what we do, compared to this length and breadth of this plate, we keep perpendicular distance between these two plates, that is small d, very small, correct? Then in that case, those two plates can be taken almost as very big planes having uniform surface charge distribution, for which intensity of electric field can be expressed by formula sigma upon 2 epsilon 0, correct? Fine. Now that intensity is always, for a positive charge, always away from it, always away from it. So for this positive charge, because it is intensity of electric field of first plate, I just show it by symbol E1, and away from this positive charge, so this way, toward the right hand side, correct? What is the magnitude? Sigma upon 2 epsilon 0, correct? Fine. Now what about this plane having negative charge? Come on, the formula for electric field of a plane of charge having uniform surface charge distribution, what is that? Sigma upon 2 epsilon 0. So here also I am writing sigma upon 2 epsilon 0, but it is due to second plate, so I am writing E2, and for a negative charge, electric field is pointing towards it this way, pointing towards it this way. So that direction is also toward the right hand side, correct? Both the directions are towards the right hand side. For a positive charge, away from it, for a negative charge, towards it, correct? Fine. Here actually what happens, at the edge of the plate, electric field is not uniform. That's why I am showing here curved field lines, correct? And that very phenomenon, having non-uniform electric field, in physics it is called fringing of electric field. Fringing of electric field, just for your kind knowledge, okay? If you keep this distance between these two plates very small, then this fringing can be neglected, okay? Fine. Now we want to find out resultant electric field in the region between the plates, and that resultant electric field I am showing by symbol capital E. You can write it this way, E1 plus E2. Why you are making straightway addition like scalars? Because these two vectors have same direction. Whenever vectors are in the same direction, you can add them like scalars. So I am writing E1 plus E2, correct? That is, E1 plus E2 means this plus this, and this plus this will give you sigma upon epsilon 0, correct? Now there is very little extra formula. In the textbook they adopted that formula directly. I am showing you how to get it, very simple. Electric field from the basic definition, don't you know? It is resultant electric force exerted on a unit positive charge. So, it is F upon Q. Now, just multiply by D in numerator and in the denominator also. Come on, I am multiplying by D here also, here also. But don't you know, force into displacement will give you amount of work done. So, force into displacement is amount of work done, capital W. In the denominator, Q into D as it is, correct? Now, tell me, work done per unit charge, work done per unit charge. What is it? From the basic definition, work done per unit positive charge. What is it? Potential. So, work done per unit charge is nothing but potential. I am writing capital V, the small d as it is, correct? Actually speaking, this is going to give you potential difference, potential difference. Why? I am showing you. For this negative charge plate, if you take potential to be 0, then for this positive charge plate, because its potential is higher than potential of negative charge plate, so higher than 0, let it be capital V. So, if potential at negatively charged plate is taken arbitrarily 0, then potential at positively charged plate can be taken equal to V. Then what will be the potential difference? V minus 0, that is V, correct? You know, absolute value of potential is not important, changes in the electric potential are important. So, here potential difference between these two plates I am taking capital V minus 0, that is capital V. So, this is going to give you potential difference, correct? So, ultimately which formula we have obtained? E equals to V upon D, and this formula in the textbook they have adopted directly. I have shown it how to get it, simple. Now, onwards, please remember, for finding electric field between the two unlikely charged plates having equal magnitude of electric charges is, what is the formula? Capital E equals to capital V upon small d, that is intensity of electric field is equal to potential difference between two parallel plates divided by perpendicular separation between the two plates. Okay. Now, onwards, please remember, E equals to V upon D, got it? Fine. Now, E equals to V upon D, that is what we have proved. So, in place of E, I am writing V upon D. In place of E, I am writing V upon D. Now, what about sigma? Sigma is surface charge density. What do you mean by surface charge density? Total charge upon total area. Just take any one plate, because both the plates have same magnitude of electric charge. Suppose I am taking this plate. What is the charge? Capital Q. And what is the area of this face? See, you should consider area of that face on which charge is present. Charge is present here only. Because charge is present here only, I should take its area only, that is capital A. So, total charge is capital Q on this face, and total area of this face I am taking capital A. Capital Q upon capital A, correct? And divided by epsilon 0 as it is. Epsilon 0 as it is, okay? Now, from this you can find out Q upon V. But before that, you please take this A down, okay? So, it is Q upon epsilon 0A, Q upon epsilon 0A. And now find out Q upon V, Q upon V, correct? Take this term in the numerator. So, it is Q upon V, it will be epsilon 0A upon D, epsilon 0A upon D. Last time we had seen the definition of capacitance. What was the basic definition? C equals to Q upon V, C equals to Q upon V. Remembered? Ratio of magnitude of charge on either plate of a given capacitor to the potential difference between two plates of that capacitor is called capacitance of that capacitor, shown by symbol capital C. So, in place of this I am writing capital C, simple. This right hand side as it is, right hand side as it is, got it? My dears, this is epsilon 0 means permittivity of vacuum. So, as long as the medium between these two plates is air medium, or if there is vacuum between the plates, then you can apply this formula, okay? But if you replace this air or vacuum by some non-conducting medium, normally we call it dielectric medium, then that capacitor is called dielectric capacitor. At that time you need to make a little change in the formula. Instead of epsilon 0, whichever medium you are placing here, its permittivity is to be written. So, instead of epsilon 0, we should write permittivity of that medium, let it be epsilon, rest of the part as it is, okay? Simply instead of epsilon 0, you should write epsilon. And remember what was dielectric constant capital K? It was epsilon upon epsilon 0, epsilon upon epsilon 0. So, what is epsilon from that? Epsilon 0 into capital K. So, in place of epsilon I am writing epsilon 0 into capital K, correct, into A upon D as it is. Got it? Fine. This is the formula for parallel plate air or vacuum capacitor, and C equals to this is the formula for dielectric capacitor. Okay. My dears, from this we can say capacitance of parallel plate capacitor depends on three factors. It depends on the type of medium between the plates, it depends on size of the plate, that is dimension of the plate, and it does depend on the relative arrangement of the plates, that is on the perpendicular separation between the plates, correct. I repeat, capacitance of a parallel capacitor depends on three factors. First, type of medium between the plates, second, size or dimensions of the plate, and third, relative arrangement of the plates or perpendicular distance between the parallel plates. Got it? Fine. Let us go for now question number 19. Series connection of capacitors. Series connection of capacitors. My dears, if you have more than one capacitor, then you can connect them in three different manners. Which three different manners? One is known as series connection, another is known as parallel connection, third is known as mixed type of connection. Mixed type of connection. Okay. About mixed type we will see later on in the syllabus of theory. Right now we have to study about first series and then parallel connection of capacitors. Let us see one by one. Here we talk about series connection. If you are given more than one capacitors and if you are asked to connect them in a series manner, how would you connect it? I am showing you. In the figure I have shown series connection of three capacitors having capacitances C1, C2 and C3. Just note very carefully how is the type of connection I am showing you. First capacitor is this, second capacitor is this, third capacitor is this, correct. How is the connection made? Second plate of first capacitor is connected with first plate of second capacitor. Then go further, second plate of second capacitor is connected with first plate of third capacitor. Suppose fourth capacitor is there, suppose, then you can say further second plate of third capacitor will be connected with first plate of fourth capacitor and so on, correct. This is how you can make the entire series connection. Got it? Now this terminals A and B, they are the endpoints of entire series connection, across which we are supposed to connect some battery. For the symbol of battery you must remember, longer terminal means positive, shorter terminal means negative. Potential difference between these two terminals of a battery, I am taking capital V. It is also potential difference between points A and B. So, I am writing VAB. A and B you should write in one line, and that whole line you must write well below capital V. Okay, fine. Now, what is the speciality of such a connection? Let us see. Speciality or characteristic feature of this connection I am showing you. Here it is found that though you may have capacitors with different capacitances, then also it so happens here, irrespective of value of capacitance, the charge on each capacitor is found to be same. Charge on each capacitor is found to be same. That's why here also I am writing capital Q, here also capital Q, here also capital Q. Then you may ask how? I am showing you. Look, in textbook this part is not explained. I have already explained in the diagram. I am showing you. Look, it is this plate which will lose the electrons first because it is connected to positive terminal of the battery. Correct? Suppose 2 electrons are lost by this plate. I mean 2 electrons start getting displaced from this plate to positive terminal of the battery. Correct? So after losing 2 units of negative charge, there will be positive charge on this plate, say plus 2. Because it is plus 2 units, I am showing plus signs 2 times. Okay, fine. Now those 2 electrons which are removed from this battery, they will flow here through this conducting wire, will enter into the battery, will receive energy, and then those 2 electrons will be deposited here. That's why I am showing here 2 negative signs. Whichever number of electrons are removed from this plate, same number of electrons are deposited on this plate. So here if plus signs is 2, then here negative signs also must be 2. Simple. Once this plate becomes negative, it will repel electrons from the opposite plate. So electrons are pushed this way. So after losing 2 electrons, the positive charge on this plate is plus 2 unit. Correct? Those 2 electrons which are pushed will be deposited here. That's why I am showing here 2 negative signs. Once this plate becomes negative, it will push electrons from this plate. So this plate will become positive. Correct? Plus signs I am showing 2. Then those 2 electrons will be deposited here. So I am showing 2 negative signs. Look. Now tell me, charge of a capacitor means magnitude of charge on either plate. What is the magnitude of charge here? 2 units. Here also 2 units. Here also 2 units. Correct? So what I mean to say, though these capacitances may be different, no problem. For each capacitor, charge is same. This is the speciality of such a series connection. If in a given connection of capacitors with different capacitances, charge deposited on each capacitor is same, then that connection is called series connection. Got it? Fine. So I written here Q equals to equal. Correct? Amount of charge is equal for all the capacitors. Now let us find out total electric potential difference across this entire series connection, that is between these 2 endpoints A and B. And that total electric potential difference is capital V. So I am writing here capital V. Okay? But you want total potential difference between these 2 endpoints, then you can find it by making addition of potential differences across each capacitor. For first capacitor I am taking potential difference as V1, for second I am taking V2, for third I am taking V3. Correct? Fine. Now what is V1? Don't you know capacitance basic formula? C equals to Q upon V. If C equals to Q upon V, then what is V? Q upon C. V equals to Q upon C. If V equals to Q upon C, then V1 you should write Q upon C1. Q upon C1. Don't write Q1, Q2, Q3 because Q is equal. Q is equal. So V1 you may write Q upon C1. Similarly, V2 will be Q upon C2. Q upon C2. V3 will be Q upon C3. Q upon C3. Correct? Come on. Q, Q, Q. Charge is equal. Okay? Take Q, Q, Q common. Inside the bracket 1 upon C1 plus 1 upon C2 plus 1 upon C3. Just give it equation number 1. Okay? Look. Now just do one thing. You remove this entire series connection. Okay? Remove it. And between these 2 endpoints A and B, you just place only one capacitor, but of such a capacitance such that when we connect same battery, we should get same charge. If we get same charge on that single capacitor, then both the circuits are equivalent to each other. Because both the circuits are equivalent to each other, we will call that single capacitor as equivalent capacitor of given series connection of capacitors, and its a capacitance we will call equivalent capacitance. Sometimes it is called resultant capacitance or effective capacitance, but this word equivalent capacitance is more famous. Okay? So now just replace this entire series connection by a single capacitor which are shown here. and across which when I connect same battery, if I am going to have same charge, then that capacitor will be called equivalent capacitor to this entire series connection of capacitors, and its capacitance will be called equivalent capacitance, which is here shown by symbol CS. S stands for series. S stands for series. Okay. What is CS? Equivalent capacitance of given series connection of capacitors. Got it? Fine. Now, from the definition of capacitance, it is ratio of charge to potential difference. Charge is Q, potential difference is the same because we are connecting same battery. So, come on, charge to potential difference, that ratio is called capacitance. But this capacitor has capacitance CS, so I should write here CS, correct? Find out V from here. It will be V equals to Q into 1 upon CS. V equals to Q into 1 upon CS. Give it equation number 2. Okay. Compare equations 1 and 2. Compare equations 1 and 2. Come on. Left hand sides are same. So, right hand side also must be same. But on right hand side Q is already same. So, this bracket now must be equal to this bracket. So, 1 upon CS should be equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Had there been fourth capacitor in series, in the same series having capacitance C4, you could have written here plus 1 upon C4. Had there been fifth, you could have written plus 1 upon C5 and so on, correct? In general, for a series connection of n number of capacitors, how would you express this result in general? Very simple. 1 upon CS equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus dash 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 plus 1 upon Cn, where n indicates total number of capacitors used in a given series connection. Simple. The same result in general we can express like this, correct? This mathematical equation itself is known as law of series connection of capacitors. Law of series connection of capacitors. How would you express it in words? Simple. Reciprocal of equivalent capacitance of a given series connection of capacitors is just equal to summation of reciprocals of capacitances of individual capacitor in that connection. I repeat, reciprocal of equivalent capacitance of given series connection of capacitors is just equal to summation of reciprocals of individual capacitances in that connection. Full stop. This very statement is called law of series connection of capacitors. Law of series connection of capacitors. Okay. Fine. Now we go for question number 20, that is about parallel connection of capacitors. Parallel connection of capacitors. In the diagram, you can see there is a parallel connection of 3 capacitors, and then across that parallel connection, one battery is connected having terminal voltage say capital V, and its terminal voltage, that is potential difference, is applied across points A and B. So, I am writing here VAB. Okay. How to make such a connection? Note it carefully. For all these capacitors, you can see their left hand side plates are connected to one common point, say point A, and for all the capacitors, their right hand side plates are connected to another common point, say point B. If you make connection in this manner, then it is called parallel connection. Okay. This one was series connection, this one is parallel connection. Got it? Fine. Now, how to get the equivalent capacitance of such a parallel connection? I am showing you. But before that, what is the speciality of such a parallel connection? Very simple. Look, speciality is that for all the capacitors, potential difference between the two plates is found to be same. Potential difference is same. Potential difference, that is capital V, is same, equal for all the capacitors. irrespective of value of capacitance, each capacitor has same potential difference between its plates. But how? I am showing you. Which are the two endpoints of this capacitor? They are points A and B, correct? For this capacitor also, its two endpoints are A and B. For this capacitor also, endpoints are A and B, correct? And tell me, between points A and B, what is the potential difference? It is equal to capital V. So you can say potential difference between these two plates is also capital V, between these two plates also capital V, between these two plates also capital V. Okay. So what I mean to say, irrespective of value of capacitance, in this parallel connection it will so happen always that potential difference between two plates of any capacitor would be equal, correct? Fine. Now, depending upon the value of capacitance, different capacitors will have different amounts of electric charge, because don't you know, C equals to Q upon V, C equals to Q upon V, but in the denominator capital V is same right now, so C is proportional to Q, or you can say Q is proportional to C. If Q is proportional to C, then smaller is the capacitance, smaller will be value of charge. If greater is the capacitance, greater will be value of charge. In the figure, suppose C3 is greater than C2, greater than C1. So C1 is smallest value, so it should have smallest value of charge. That's why I am showing here only one plus sign, only one, and here only one negative sign. Compared to C1, if C2 is greater, then here amount of charge you must show greater. Here I am showing two plus signs and two negative signs. Okay, and if C3 value is the greatest among these three, then it should have maximum charge. Here I am showing you three positive signs and three negative signs, correct? So here the potential difference is same, but then C equals to Q upon V, V is same. So now C is proportional to Q or Q is proportional to C. So smaller is the capacitance, smaller is the charge, greater is the capacitance, greater will be charge. Amount of charge stored here, suppose it is Q1, here Q2 and here Q3. Why don't you add all the values to find out total charge stored in this entire system? Let it be capital Q. Q equals to Q1 plus Q2 plus Q3. Here you are finding total potential difference, and here you are finding total charge. Okay, fine. Q1 plus Q2 plus Q3. C equals to Q upon V. Then what is Q? C into V. Q equals to 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 C into V. But this is parallel connection in which potential difference capital V is same. So here also V, here also V, here also V. Okay. Don't write V1, V2, V3 because V is same. V is same and equal. Okay. Take V common. For Q1 you may write C1 into V. For Q2 C2 into V. Q3 C3 into V. Now take V common. Then inside the bracket C1 plus C2 plus C3. Give it equation number 1. And now the way we had replaced the connection by equivalent capacitor, here also we have to do the same procedure. Remove this entire parallel connection, just remove it. Then between these 2 points A and B, you are supposed to put only one capacitor of such a capacitance such that when you connect same battery across that capacitor, you should get same total amount of electric charge, that is capital Q. Really, if you get same amount of electric charge, then that single capacitor will be called an equivalent capacitor to given parallel connection of capacitors, and its capacitance will be called equivalent capacitance of parallel connection of capacitors, and that's why I am putting the symbol CP, P for parallel, P for parallel. Okay, fine. Now from the basic definition, C equals to Q upon V, C equals to Q upon V, but instead of C I should write CP, correct? This is going to give you equivalent capacitance of given parallel connection of capacitors, correct? Fine. Now find out Q from here, it will be V into Cp, V into Cp, V into Cp. Give it equation number 2. Now from 1 and 2, come on, compare. Left hand sides are same, then right hand sides must be same. Then on right hand side V and V they are same. So Cp must be this much, that is C1 plus C2 plus C3. Had there been fourth capacitor in this parallel connection, then you could have written one more term plus C4. If fifth capacitor is present, then plus C5. In general, for n number of capacitors connected in parallel, how would you express the result? Cp equals to C1 plus C2 plus C3 plus dash 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 plus Cn. Correct? This very equation itself is known as law of parallel connection of capacitors. Law of parallel connection of capacitors, and that is why I have written here law of parallel connection of capacitors. How would you express it in words? Very simple. Give the statement of this law in words like this from this result. Equivalent capacitance of given parallel connection of capacitors is just equal to summation of individual capacitances in that connection. Full stop. This very statement is called law of parallel connection of capacitors. I repeat, equivalent capacitance of a given parallel connection of capacitors is just equal to summation of individual capacitances in that connection. Full stop. This very statement is called law of parallel connection of capacitors. Got it? Fine. Now we go for question number 21 about points of difference between series connection of capacitors and parallel connection of capacitors. My dears, the concepts cleared in this particular question will help you later on, and I must appeal to everybody, you please take very special interest while understanding this particular answer, because if you refer any reference book, if you refer the points of differences between series and parallel connection of capacitors, there hardly you will find 4 points of difference, maximum say 5, not more than 5. Here I have just taken enough pain to think for that, and I have prepared maximum number of points of difference, and that came out to be 11. So I have thought this much just for the sake that I wanted to cover every point. So I have taken very special pain for preparing this answer. I just appeal everybody to understand and then after to remember. Please take interest. Look, point of difference I will write here, and here I will write for series connection of capacitors, here I will write for parallel connection of capacitors. Let us see one by one. First point, speciality. What is the speciality of series connection of capacitors? Just now I said, irrespective of value of capacitance, amount of electric charge deposited on each capacitor is same. That's why I am writing Q is equal. Correct? What is the speciality here? Irrespective of value of capacitance, potential difference between two plates of every capacitor is same. So V is same. Correct? Equal. Second, about law. What was the mathematical form of law of series connection of capacitors? Just now we wrote here 1 upon Cs equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus dash 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 plus 1 upon Cn. Correct? 1 upon Cs equals to 1 upon C1 plus 1 upon C2 plus dash 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 plus 1 upon Cn. Correct? What was the mathematical form of law of parallel connection of capacitors? Cp equals to C1 plus C2 plus dash 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 plus Cn. Cp equals to C1 plus C2 plus dash 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 plus Cn. Correct? Fine. Here if you speak in words, then reciprocal of equivalent capacitance is equal to summation of reciprocals of individual capacitances. Here equivalent capacitance is equal to summation of individual capacitances. Got it? Let us go for now point number 3 about value of equivalent capacitance. Here value of equivalent capacitance is found to be smaller than smallest among given values. Smaller than smallest among given values. Here value of equivalent capacitance is found to be greater than greatest among given values. Greater than greatest. Here smaller than smallest, and here greater than greatest among given values. Okay. What about if you increase the number of capacitors in the connection? In case of series connection, as you go on increasing number of capacitors, equivalent capacitance goes on decreasing. As number of capacitors is increased, equivalent capacitance for series connection symbol is Cs, that goes on decreasing. Here, as number of capacitors is increased in parallel connection, equivalent capacitance goes on increasing. N increases, Cp also increases. Here N increases, Cs decreases, but here N increases, Cp increases. Okay. Then what about polarity of the charge for the plates which are interconnected? I am showing you. Here these two plates are interconnected, correct, through this wire. Tell me, what is the polarity of the charge here? Positive, and here negative, correct. One plate is having positive charge, another plate is having negative charge, means they are unlike charges, correct. For these two plates, they are interconnected by this conducting wire. You can see polarity of the charge, here positive, here negative. So here you can say polarity of charges between the connected plates are opposite. One is positive, rest is negative, correct. So unlike charges are found to be present on the connected plates here. What about here? Come on. This is first plate, I mean for the first capacitor, this is the left hand side plate. This is left hand side plate of second capacitor, left hand side plate of third capacitor. They all are interconnected at point A, and all of them have positive charge. Here also positive, here also positive, here also positive, correct. How to find these right hand side plates? They are interconnected at another point B. They all have negative charge. You can see here also minus, here also minus, correct. So here interconnected plates have same polarity of the charge, and here opposite polarity of the charge. I repeat for the last time, in case of series connection of capacitors, the interconnected plates have opposite charges or unlike charges, and here interconnected plates have like charges, Look, what about if you remove one capacitor? What about if you remove one capacitor? If you remove one capacitor from this series connection, then other capacitors do not get charged, correct. If you remove one capacitor in a series connection, charging of other capacitors also gets stopped, okay. Here you may remove one capacitor, correct, then also the charging of other capacitors will continue, okay. What about junction? What is called junction? That you learn in third chapter, but let me tell you, is very simple. A point in a network or point in this circuit where more than two conductors meet is called a junction. I repeat, a point in the circuit where more than two conductors meet is called a junction. Not two, more than two, okay. Tell me, is there any junction here? No junction, because at no point you will find more than two conductors are meeting here, correct. So there is no junction here, there is no junction. So I am just putting wrong mark, there is no junction, okay, no junction. But here, come on, at this very point, how many conductors are meeting? 4. Look here, 1, 2, 3, 4. Means more than two conductors are meeting, so it is called a junction. Here is one junction, here is one junction, so there are two junctions. So there are two junctions, okay, fine. What is the reason for decrease of equivalent capacitance when we increase the number of capacitors in a series connection? I am showing you. As you go on adding more and more capacitors in a row in this series connection, what will happen? The separation between first and last plate, will keep on increasing. If separation between first and last plate keeps on increasing, naturally the perpendicular distance between first and last plate will go on increasing, and if perpendicular distance d is increasing, naturally capacitance will decrease. So that is the reason, okay, from physics point of view, fine. What about reason for increase in equivalent capacitance for parallel connection as we increase the number of capacitors? I am showing you. Here, as you go on increasing number of capacitors in this parallel connection, the effective area on which the charge has to be deposited keeps on increasing. And if effective area goes on increasing, look here, if area of the plate goes on increasing, naturally capacitance will increase, correct? Fine. So here perpendicular distance is increasing, so equivalent capacitance decreases. Here effective area of the plate increases, so equivalent capacitance also increases. Fine. What about order of getting charged? Here first of all it is this plate which is getting charged up, and the same charge is deposited here. So this plate is getting charged in the second order, then this plate, then this plate, then this plate, then this plate. Okay. I mean to say, in case of series connection, different plates get charged up one by one, ton by ton, okay, not simultaneously. And here it so happens, as soon as you connect this battery, all these plates, they start losing electrons at a time simultaneously. So here charging of all the plates takes place simultaneously, and here charging takes place one by one, ton by ton, okay. What about connection of a battery? Here battery is connected across first and last free plates which are not connected with other plates. These plates are interconnected, correct? These plates are interconnected, but the free plates are at the two endpoints of the entire series connection, and across those two plates this battery is connected. Here battery is connected across two common terminals where left hand sides and right hand side plates of parallel connection are connected. I repeat, here battery is connected across those 2 points where the left hand side plates and right hand side plates are interconnected. Okay, fine. What about charging current? Whichever current flows during the process of charging, it is called charging current. Here charging current, we normally take it from positive to negative this way. The charging current here will flow this way, from positive to negative. It gets only one path to flow. If you are talking about flow of electrons here takes place this way. It also gets only one path to flow. Here what happens? Electrons will flow in this path also. Look here this way. For second capacitor, electrons will flow this way. For the third capacitor, electrons will flow this way. Correct? So I mean to say, here charging current gets more than one path to flow. Here charging current gets only one path to flow. Here charging current gets more than one path to flow. Got it? My dears, I once again remind all of you that please prepare all these points of differences between series and parallel connection of capacitors very nicely. I have taken very special pain to prepare this depth of this article. Please, okay?